So let's get this party on the road. Wow! Awesome. We've all made progress. How many people have started this assignment? Good, okay. No one's not raising your hand? Start the assignment. So it's due on, what did I put, Tuesday night. I think I may have put some conflicting dates somewhere, but the intent was Tuesday night. We're using the Google Doc as kind of a master deadline schedule. Is it Wednesday night? What are, it's at Google, up to the Google Doc. Let's see. Let's just open that up. So Monday's Labor Day, and where is it? Sheets. I don't even know what I'm opening up now. Okay. Computer security. Let's just find this out. No. 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 There we go. Okay. Is that, am I right or am I right? That's right.
It almost looks like 9-5.
It almost looks like, yeah, so maybe I should actually attach a real date to it, shouldn't I? Yeah, so the intent is that there's like a date over here, right? Like, Tuesday night. Okay? Okay, I can make this really big. Okay, anyway, so let me try to be a little bit less ambiguous about this and have like the same date everywhere. I think somewhere it's due on the second, so don't freak out. On the Tuesday night for this month. Does that make sense? So the people who started this assignment, fun? Yes? Yes? It's fun, right? Yeah. It's really addictive. Like you really do get into the whole hurt lockers. And I've heard like there's traumatic tales of people who are just like tinkering like with this bomb in the net, and then it like blows up, and you're like really freak out because it's like it notifies the instruction, boom, and yeah, it can be very intense, which is fun. Other announcements. So let's see, Aaron here was asking when his office hours would be, but I have office hours right after this class. So if you have any questions, or if you're still going to debate on whether or not to take this course and so forth, we can talk about it at 1. I'm up in E416. You can check out the website for the course, or the Piazza. I've seen the Piazza has been extremely chatty. Nobody's asked anything. But I'll be posting announcements and stuff to that. What else? There's a book that is not required, but it's kind of just, it's nice. It's called, what's it, Hacking Progress Petition? That's the name of it. So this is quite nice. It actually talks about all the kind of learning stuff that you need to know to get up to speed, so it might be worthwhile checking out. I think there is an electronic version. So you can check that out. There's also the book that comes to web stuff is called The Tangled Web by Mikhail Solevsky, which is also a very good book that I recommend. Any questions before we get going on the assembly train? Yeah.
Those CS app readings that you list.
Yes.
Are we actually supposed to do those, and how?
You don't have to do those. They are if you have absolutely no idea what I'm talking about.
Oh, okay.
They're just like chapters in the Computer Systems of Programmer's Perspective book, also available online.
They can't all be accessed like from that little sample they have.
Oh, I see. It's so simple.
I'm just wondering. It's not a big deal.
I have a copy, and so there are some copies around. We've been using in some of the places where I taught this course. It's really just a question. It's a resource where you can look up stuff about assembly if you want to know a little bit better. I also posted some on the website, and I think somebody did post on Piazza the useful GDP. Posted a useful kind of GDP summary and some notes about activity. Yes.
So I have a real quick question. So when you're using the debugger, the thing has to be pre-compiled. So every time you compile, the program would just fix, right? So can you run the debugger without compiling it?
So the way the typically works is that you've taken your source code and you've compiled it, and you have this binary. And now whenever you run the binary, you start like a process. And that's exactly what the debugger does, is that it starts the program and then it attaches to the process that's running, right? So the way the process, this particular bomb process works is that it expects 6 strings of input. And you can have the debugger start up and like read in like 3 sentences or 4 sentences from a file or something when it opens up to get you to the phase or stage that they need to be in, or something like that. But it starts anew every time you rerun the program.
So running a debug means compiling programs. That will
No, you actually, you will never have to compile this program. It's already been compiled for you. You're simply running it. It creates just a program instance of it. Make sense? Now, we did provide you with the C file. If you do try to compile a C file, you may ruin your bomb, and then you talk to me, oh, you made my bomb is broken, right? It's completely diffused. Then I can give you a new bomb, and that's no problem. Okay? Other questions? You said you had 2 questions. I heard 1 thing. Oh, okay. Other questions? Yeah, go ahead.
Where do we get access to the videos?
Yeah, that's good. So I've been putting these videos on YouTube kind of unlisted, and I'm thinking about just posting them on like the Piazza track. Does that make sense to people? Either that or I'll just create a YouTube playlist and the playlist link, and I'll just add to the playlist. Make sense? Okay. Other questions? No? Okay. So all aboard the x86 train. Great. Okay. So. Yes, this would be a lot of kind of just like mundane information. You can imagine you're in like med school learning about something completely esoteric. But we'll have these 2 to 3 lectures about x86, and then we're going to be going more into kind of thinking mode rather than just like arith mode. Okay, so arithmetic operations. This is where we left off last time. We were looking at that you can do a whole bunch of stuff with all this. With your CPU, you can take your different register, you can add them up, you can subtract. Extremely exciting stuff, right? So. And you can shift them around. So let me give you an example of what happens. So remember that the assembler actually does all kinds of weird stuff. So here's an actual C program over here. It has these 6 variables here called T1 through 5 and then Tval. And it's doing some arithmetic or some calculations. Now let's look at the assembly code that corresponds to it. Because when you're doing reverse engineering, this is all you see here on the right-hand side. So you wonder, what was the original program that you were compiling to get to there? So let's have a quick look here. So while we're looking at it, let's make sure that we know also what's happening here with respect to the memory that we're accessing. Remember, we tend to have this very common prologue here where we're accessing something that's 8 bytes away from EPP and 12 bytes away from EPP. Let's remember what this was. They're the parameters to the function. So somebody calls arith, and they have to provide x, y, and z. And in 32-bit assembly, they've been pushed onto a stack, which we haven't talked about yet. They've been pushed on, therefore they're accessible in the stack frame above us. So, and it's separated by this thing called the frame pointer over here. So actually, the standard way to get x here is 8 bytes away from you. 12 bytes would be the variable y, and then at 16 we have z. Great, okay. So that means that we understand these first few things here. We know that x and y here are now being stored in the local registers ECX and EDX. Okay? And now what happens? Let's just look at it without coloring for now. What on earth is this thing over here? Lil, EDX, EDX to EX. What are we doing? Okay.
So you're loading what's in the EAX register into that memory address?
All the way around. We're loading the output of this calculation into EX. And what is the thing that we're putting into EX?
Go to memory EDX and then 2 EDX sizes up from that.
Right, exactly. Except we don't actually touch on the memory. We just look at the address that would come out of it. But what is this thing over here? So we know that EDX here is Y. What's happening here? Well, X isn't touched because ECX isn't referenced here. What is happening?
What is happening?
And how on earth does it correspond to anything that's up there? It's funky sounding. Yeah?
I think what it is saying is y plus y times 2, so it's y times 3.
So it's multiplying y with 3. That's great. Why? Why are we multiplying y with 3? Yeah, so let's sort of think about, like, what might it be trying to do?
In the line, T4 equals y times 48. So 48 is 3 times the power of 2. So if you multiply by 3, then later you can just shift by
Yeah.
4 to 2 to 14.
Specifically, it's 3 times 16. So here, we're actually shifting something by 4 to the left, which is like multiplying it by 16, 2 to the 4. Right? Okay, so these two things here correspond to T4. We haven't even touched T1, T2, T3 at all, right? So we're doing things completely out of order. And that's a part of what your compiler is doing. Your compiler is looking at like, okay, what is the fastest way I can go through this, right? It like takes your code, like fragments things around, and like really crushes it down into something that's extremely optimized. And as a part of the optimization, to figure out that like, hey, I can take this thing here, I can use this really quick CPU routines to calculate 48 faster than I could use integer multiplication. And then I'm just going to move on to do what? What is this? Little 4 of ECX from EX to EX. Come on.
X plus y.
X plus y. So this is x plus y, but this isn't y anymore. It is, well, it's already multiplied by 16 as well. So it's the 48 times y. Which actually is called T4 over here. Right? So here's T4. And what is the VCX again? X. So it's x plus T4 plus 4. Any takers?
That's D5.
Ah, it looks a lot like T5, doesn't it? So in fact, it's actually T3 and T5 together in a single command. Because, you know, you can, right? So it didn't even create a variable for each of these 6 things that we declared. It didn't have a register for it. It didn't need to. So that had to do 2 operations to get the 48, but they were very fast operations, and 1 to knock off both T3 and T5. Now what's happening here? Here's an add. We're adding ECX is what? It's okay. And we're adding into what's an ECX? Still Y, and we're storing it in. So what does this correspond to? T1. This is X plus Y. Now finally we get to T1, right? Okay. And then we have add 16 EBP to EDX. T3 plus T4, right? So remember we stored, actually no, is that right?
That's Z plus T1.
This is Z plus T1 that's being added up here. And we're storing the result in EDX here. And then we multiply the result of that EDX here with the result of EAX, which is a computer here. So we're doing the return value here. And lo and behold, it actually ends up in EAX, which is our return value per contract. That's super dense, isn't it? Right? So we can color it up so we can just remember what it is. So here are the colors of the different routines. So T1 over here is the red one down here that we do like almost next to last. The return value here is this kind of color that I can't describe the name of, some sort of orange, dark orange, brown variant. Green is the one that we started off with here, which is 2 commands over here. And you can see that the T3 and T5 were blue, and they actually became a single implement. It's really wacky, right? Now, think about this as being hard, and then think about what virus and malware makers and actually people who don't want their software to be cracked, what they do to try to make this harder. Right? So anti-debugging techniques. So they obfuscate things. They add stuff you don't need. They add traps. They add things that like store your computer if you tinker with them. Even Skype, when you open up Skype, it has this code that looks like malware that actually scans your computer and figures out your BIOS ID and all sorts of wacky stuff just to kind of like make sure that you're not running in a debugger, you're not trying to decrypt Skype, it was supposed to be encrypted until recently. All sorts of weird stuff like that. It's a funny game. Anyway, so that's a few things here. Now, if you were just to have a single method over here that says x plus y plus z times x plus 4 plus 48y, you get the same exact assembly code. Cool, huh? Nice. Good. Okay, so we talked a little bit about registers so far. We talked a little bit about some of the instructions that we can do. Now let's talk a little bit about these condition codes. This last part here of the sequence. Okay. So far, our world is extremely boring. We're kind of like a commodity calculator. You know, the thing that you can't bring on board airplanes, right? That, well, at least not during takeoff and landing. Until recently. Now, when you take off and land, you can have your calculator can do stuff. So if anybody takes one over. Has anybody ever seen anyone bring a calculator and put on your calculator? I've always wondered about this, right? There's like, please close out calculators and laptops and phones. Anyway, so right now, you can do everything that a calculator can do, which is add up stuff and subtract stuff and store it. That's not really Turing complete, right? That's not really giving you a full program, right? You can't check your Facebook with this. So we're missing something. We're missing all the jumps and all the fun stuff, right? And if we want to jump, probably we want to jump not all the time because that doesn't really make any sense. We want to be able to have conditions under which we jump. So that's why we have condition codes. So remember, we have these registers over here, the general purpose ones, and we have the stack pointer and frame pointer, and we have a special instruction pointer so we really can't access. We just can modify it. And then there's this one extra register over here which has been broken up into little flags. So just like binary numbers. And they're called CF, ZF, and all that stuff. These are called condition codes. Now, what are they? Well, they are flags that effectively say the last thing that you did, the last arithmetic operation that you did, had the following consequences. The consequences could be like, hey, this stuff was really big that you added up. In fact, so big that I had to do a carry. I had to carry one. Or there was an overflow of your signed number. In fact, your signed number was so big that I now have a really big negative number. Or it could be the result of what you did is 0, which is very useful. And yeah, is the sign flag set, is the overflow, and so forth. So for instance, this actually happens implicitly when you do things like add. If you say add, hey, I want to add A and B. Well, we only have 32 bits to play with, so it's possible that A plus B might be a really big number, in which case some of this stuff might get set. In fact, if T is equal to 0, we set the 0 flag. If the carryout, if this is an unsigned numbers here, then the carrier is going to say like, well, actually, when you add these numbers up, you can't even represent the output in the 32 bits. They're too big. Okay? If the whole thing here ends up as being a negative number, you get the sign flags, or sign flag. And then if this condition here holds, meaning that like I actually had 2 positive numbers, but the result is for some mysterious reasons negative, or hey, I had 2 negative numbers here that I added up, or subtracted results and ended with a positive number, then something funky is going on, we get the overflow, signed overflow factor. Make sense? So the intent is that you can do these things and then you're supposed to check them, but of course, nobody checks these things. That's why we have this class, right? Because we can hack stuff because nobody checks anything, right? And also remember how just on 2 slides ago we had assembly code that used LEAL and stuff. Well, one of the reasons why LEAL is fast is because it doesn't set this stuff. So when I multiply something by 48 using LEAL and shift and so forth, I have no idea whether there was an overflow. Because LEAL is not supposed to be used for arithmetic. It just happens to be really fast at it. And speed does that. Trumps a lot of things. You could even set these things explicitly. And we have this command here called compare, or CMP. And the idea here, you do some arithmetic, or maybe you're in a loop. You're in a for loop or something like that. And you want to try to see if you've made it to the end of whatever you're doing. Then you can compare here A and B. Except, of course, just to make these things slightly more confusing and also amenable to having exams. So it's questions like, hey, what does this compare what is the order of parameters for compare? You start with B before A. So you compare B and A, which is effectively like subtracting B from A, or A minus B. So what does it mean? It means that if I want to compare two numbers, this operation here will set the 0 flag for me if they happen to be equal. In other words, if the difference happens to be 0. It will set the flag, carry flag, if the subtraction here happens to be, happen to end up with a number that you can't represent, like if you subtract a too big a number from something else. Or if the difference here is 0, you get the sign flag. What would this imply here? So compare A and B, and I get the sign flags. It needs to be greater than A, and strictly. And I also get the overflow flag set here. Okay, so it means that we have alternate signs here. And there's another instruction here, the sans compare, that's called test. It works almost the same way, except instead of doing subtraction, it does an AND operation. So it's just comparing what flags are set before. So the intention here is to work with bit vectors, right? So the only things that are really set here that are important for you is, hey, are both these numbers 0? Being A and B are 0. And then, is A and B is a negative? Which would mean that both of the numbers are negative, right? It means that both of them have a sign flag set, sign flag set. And you can even play a little bit more around with this, and you have this little instructions here called set. Now, what does set do? Set takes the last thing that you did, like an add or whatever it is that you were doing, some arithmetic operation. You can set a register based on the output of that operation. So for instance, if the last operation happened to provide you with the 0 flag being set, you can say here, set E, comma, register BL or something like that, which will set the lowest byte of the EBX register to 0 or 1, depending on whether or not the 0 flag was set. So in other words, if the last operation ended up being 0, having like a, for instance, if you had a compare or if you had an add and the result happened to be 0, you will now have the number 1 in register EBL. That's a little bit abstract. Let me take an example here just to clarify things. So let's see, we do here, like, let's say we do add EBX, ECX, right? And it just so happens that the numbers were, like, EBX was equal to like 5 and ECX was equal to minus 5, right? This is the input that I got into it. So what's going to happen after this add operation is that, among other things, the 0 flag is going to be set to 1, because the result is 0, right? Now I can do, there you go. We can set, we can call this in here, set equal EDL. And what's going to happen here is that now, if you look at the ETX register, it's being kind of 4 bytes. There's going to be something, there's going to be something, something, something. And there's the least significant byte, it's not going to be 1, because the last thing that you did was equal. In other words, the last operation that you set ended up with a 0 flag equals to 1. Making sense? It's probably better seen as an example, but you can do this for all sorts of things. The suffices that we're seeing here, the E and NE and all that stuff, those actually come up all the time. Set if something is greater, set if something is negative or sign. Set if something is above. Wait a minute. I just said set if something is greater and set if something is above.
Sign versus unsigned.
Oh, yeah. So that's another cue for you if you're trying to figure out if the numbers that are being worked with are signed or unsigned, is what are these suffices of these comparisons that we're doing? If we use above and below, it's unsigned. If it's greater or less, it's signed. And notice how the actual formula of what he's trying to do is trying to see, like, hey, it's above if I know that neither the carrier flag nor the 0 flag were set. Or I know it's greater if the XOR of the sign flag and the overflow flag, so if they're not both set at the same time, And it's not the case that the 0 flag is set and then you negate it. You like do this arithmetic to try to figure out exactly what happened, right? And the output of this bit operation over here is the value that gets set into the register that we specify as an argument to the set operation. Ta-da! Cool. So here's an example. We have a little function here. All it does is that it takes x and y and tries to see if x is greater than y. That's it. And they're both signed integers, right? So the code would be, let's get the arguments. So here it's 12 EBP, which would be second argument, y. Let's get that into the AX. And we compare it to x. Notice the order of arguments here for compare. Remember, compare this b comma a. And we take, and then we're looking at, yeah. So we're looking at the result. So x minus y, if that difference is greater than 0, then set the flag, right? That's what set greater here means. So in other words, AL is true if x is greater than y. Making that sense? So there's a lot of, like, it can get really confusing really fast when you're like trying to reverse the order of the arguments and all that stuff. Now, this set operation here just sets 1 byte of a register. But sometimes we want the whole register to be that number, right? We have 4 bytes, we set one of them. We kind of want to make sure that the other 3 are not in the way, because they could be whatever you were computing last time. So we have this operation here called move 0 bytes long. It just says that, like, I'll take everything that's not AL from AX and set that to 0. Just fill it to 0. Some weird operation, but it exists. So this whole thing here is just going to do the comparison of the two numbers, and it's going to set a 1 byte register called AL, and then include the rest of the register, and that's your return value. That's your 0, 1 truth value that you're returning here in the C file. Make sense? How many people find this to be like hilariously easy? Okay? How many people with me? That's another question. Okay, that's a better question. Okay, so given that, we can now start to move into a territory where we can do some jumps, right? So just like we could set stuff, we can actually now change the program execution based on output from these comparisons, or output from arithmetic operations. In particular, we have this thing called jump, which will always unconditionally jump to some other place in the program. Or we could jump if things were equal. For instance, we're comparing, we're in a for loop, we have this I, and I is supposed to be less than 10. We compare I to 10, and if they're equal, we could jump when they're equal and go out of the loop. Otherwise, we could jump if not equal and continue the loop, right? You see where we're going with this. Same thing here, jump if something is signed, jump if it's less, jump if it's below, and so forth. So for instance, here's a little program that's just supposed to find the absolute value difference between two numbers, right? Like L1 more. Okay? So because we have the absolute value operator, we need to have a branch. We need to have an if sentence in this thing here. So we're checking to see whether or not x is greater than y, in which case we look at the difference as being the positive value x minus y, otherwise we look at it as being the positive value y minus x. Let's implement this in assembly. Okay? Let's just do it together. How would you do this? Here's something here. Here's my absolute value. Okay, I'm implementing something in assembly. I'm going to be a human typist. I'm going to write down your assembly. I will not do a lot of syntax highlighting. I won't do any compilation things. I'm just going to write stuff down. Help me out. I'm your medium. Don't make me do anything obscene. Yeah, x and y are on the stack. So we're going to access it. We're going to somehow move them out of where they are to deal with them. What do we type? Move. EBP. So we have to specify the leg. So move L. There's an EBP. So that's going to be like this.
Any register will be like J preferences.
Somebody make a decision. EAX, great. Okay, next one. What? Huh? Move. We're moving something. To EBX. Okay, wonderful. We've done amazing job here. Okay, so far we know that EAX is equal to. What is the value here? Like, this is y, and this is x. This is just for us here, right? Okay. Great that we have AX and so on. Just like, I'm just going to make an executive decision for you guys, just your own sake. I'm just going to flip this around a little bit. So EAX is x, EBX is y. Okay? Just for kind of like internal ordering kind of thing. Now what do we do? Sound Oh, CMP, sorry. Compare, somebody said?
Yeah.
EX. EBX, okay. So this means that we're doing kind of y minus x is going to, remember it's b comma a, right? So what do we do next? Jump if this is greater to, let's call it label, or like a head. Here's a head, it's a label, okay? And what do we do if it didn't happen, if it's not true? So here we're assuming that if y minus x is greater than 0, which means y is greater than x, which means that we're supposed to be now doing what? Subtract. You can see why we actually employ computers instead of people for making us understand, right? Uh-huh. So you see EBX comma what? Yeah. So what do we have here? EBX, EX. This means that we took y from x, right? So like this, and we say EX equals this, right? All right. So we need, we need to jump, okay? But, okay, so we're jumping ahead so that we don't also do the next thing. And what's here in the head? Subtract. And we're going to need to have it end up in what register to return in? So move L, EBX, EX, okay? So this is now EBX equals to y minus x, isn't it? I get these confused all the time. Okay, and we're in the final. What do we do? Yeah, previous return. Okay, let's see how we did.
You're laughing?
No, we're fine. So, something similar here. Oh, there's EBX and EX, okay? So we compare y to x, so we get x minus y. And if it's less than or equal, we jump ahead. So we're just going to, we flipped 2 orders so far. And we do exactly the same thing within the branches. It's just that it's really easy to get confused what is the source and the destination thing. Because even subtract is a little bit elusive like that. Destination from the source, right? So here are the bodies. So if we think about exactly what happened here and what we had to all do together was that we took the program in this if sentence, we broke it down into the following piece of code. We said that like, well, instead of saying if x is greater than y, let's just say that if it's less than or equal, we're just going to go to the else branch. Right? And then we do whatever we intend to do otherwise, and then we go to the exit. And we're introducing Goto. This is actually what happens with a C compiler, right? And how many people here have used Goto in any program? Ah, yes. So it's generally considered bad coding style, and that's a very mild way of putting it. I'm going to put this ugly copy here when it's in fact, like the go-to statement. There's an article called "The Go-To Statement Considered Harmful" by Dijkstra. Edward Dijkstra wrote this back in the day, where he argued that you could take any program and you could use while loops, if sentences, and for loops to get exactly everything done. You never had to use Goto. And it became extremely influential and crushed a lot of the programming languages that really looked like spaghetti code. What has happened since is that it's become banished as kind of like an abomination, Goto, right? So in fact, like you get these types of things. You go to something, you go to hell, you just don't go to more. You get an XKCD here, it's like, oh, again, it's very tempting at some point, you're like, oh, it would be really nice to get out of all my linked things and just one Goto. But be very careful, right? It could be eaten by a velociraptor. Now, if you look at the Linux kernel source code, you'll actually see Goto all over the place. And initially when people see it, they skip a beat and they like sweat profusely and so forth. There's actually a real reason for why it's done. It's because you actually get nicer and faster assembly code as a result. And it's also the case that oftentimes when you're doing something in the Linux kernel, you're effectively doing something that's kind of transactional. You're trying to do something and then do something more. And at any point of the way you could fail. And right, you've done these 5 things, you've changed something in the system, you've moved things around. And you don't want to just fail in the middle of that, right? You want to be able to kind of go back and undo everything that you did once you failed. And so the Goto effectively allows you to do that. It was just terrible that that's the reality of it, but that's actually a faster way of accomplishing what they need to do. So I'm going to use Goto here because that's what happens in the compiler, but I will sweat profusely when I do it. I'll put this like ugly color. Anyway, so here's the coloring of the different units here. So the blue stuff here, the strands over here, that's what's happening down here, and then we have the purple one down there. So we're done with that. Now, we know how to do if sentences. Cool, right? So with an if sentence, what's the next thing we should be doing? Let's do loops. So what's the most basic loop? So do while. How often do you guys use a do while loop? Yeah, exactly. Kind of more like a while kind of guy, right? Now, what does this code do here? It's written on my hands. So if you look at the code, what it's trying to do is that it takes in this number here, x, and it just says like, hey, it's the least significant bit. Is that set? Oh, it is. I'm going to add it to my p count over here, or result. Okay. And then I'm going to shift it by 1 bit. So I'm taking the bit away, and I'm continuing until I have no more bits to do it with. So I'll end up with number that's 0. It's very handy that this is an unsigned number. If it were a signed number, you might be doing this for a while if it's negative, right? Anyway, that's a do while loop. Constant number of ones. Here's a fun question for you guys. Can you, in a single bit expression, count the number of zeros? Sorry, the number of ones that are set in a number? That's a hard question. I'm not expecting it to be like, yeah, it's an actual kind of algorithm. It's something that you can do without a loop. Just something great to think about. Anyway, so here we're using a loop for it, which is perfectly fine. Let's try to convert this to something. So what do we need to do? Sure, can we just go ahead and implement this? Da-da-da. Da-da-da. What do we need to do? I have a blank sheet of paper and writer's block. What do I do?
Use a GCC with an S flag.
I know it's a hacking class, and I know I'm supposed to encourage you guys. Let's do it from scratch. So what do we do? Okay, so at least we got our cover our bases, right? Let's get our EDX register to contain X. Okay. So this is here now X. Okay. What now? We're going to need something to count stuff for us, right? So what do we need to do? I speak only assembly. Of. Oh. Bovu. Ha ha ha. EasyX 0. Yeah, so that's Intel command, right? And if I do this, this is actually going to be like, oh, what's in memory address 0? Brrr, segmentation fault. So we have to be very careful here. Think. Haha. The immediate value 0, right? Now there's an alternative way in which you can do it, which you'll see all the time, which I'm going to write here. XOR something with itself. Why am I showing this trick? Because it will come up. Yes, it will. Good. Okay, so XOR, now ECX is 0. What do we do? A label? Request timed out. So somehow we're going to get the lowest bit, right? Right? So we could take our x here and we can say and, right? And b, we could just take the byte here. And byte e, what do we write? What are we doing? Like the, oh, if it's b, we're just doing the 8-byte one. We could say have a long one, but let's say the byte one just for fun. And b, where's the lowest, least significant byte of x? It's in DL, lowest part of EDX, right? Lowest byte. So, and we're going to need to end that with the number. We're kind of in a, we're trying to accomplish something 2 months here. We're trying to take a register and the value, and we want to store it somewhere. It's problematic, isn't it? So, any ideas? Set a flag is very interesting. We could do the flag setting, right? That could be really fun. How do we do that? So, what was your suggestion, Jerry?
Just making a second copy of it. And
yeah, we can. That's always safe to do, right? So we could say like move BDL to like I don't know BL, and then you can do kind of and BL. We can store it like and BL. Now you have it over here. Now you just add BL to whatever you want, I guess, ECX. That'll probably do it, right? But let's do the flag setting route. Oh, I don't know, it just vanished. Okay, help. Okay, I need to set a flag somehow. How do I do it?
Set EDL.
Set EDL. Okay.
Oh, it's on one.
So the thing is that it's set is setting something in DL if the last operation that you did resulted in setting the register of the ZF condition code, right? So somehow we need to make sure that gets set through something, right? But we could do it like, we could have a test or something that explicitly sets it, right? Test L EDX what? Right? And then they're not supposed to be exactly, so if it's 0, we're out of luck, right? So we want it to be set if they're equal, it means that the value that we're doing and 1 was not 0, right? Because it has to be that the whole thing, the difference, the A and B from the testing returns 0. Then you set the Z flag to 1. So we want it to be the negation of that, right? So we want to have it to be set any, right? And we don't want to overwrite DL because we're kind of using that stuff. So I'm going to set it to Yes. So what did you say?
BL?
BL, yeah, something like that, right? And then we do same thing as before, right? Add B, BL to ECX, right? Nice. Of course, we didn't say anything like this, we just did the same thing twice, just in two different ways, but it's cool. And now we need to do something more. Shift. And is it arithmetic or is it, what's it called, what was it? Arithmetic right or left? What are we doing? We should do the left or to the right? Shift to the right, okay. That's left for me. Okay. Shift something right. L, I guess. And what's the register? EDX, okay. And am I doing it arithmetic or logical? Why?
Logical is inside.
Oh yes, this would be very, very useful. So just shift right L. Otherwise we're going to be trapped for a while. And now what do? We have to finish our loop. Yeah. So shift, well, does shift set stuff? That's the question, right? Does it set the condition code? And let's have a look at our beautiful slide deck here and find that out here. What sets stuff here? Test, compare. Not set by Lee, well, that's fine. But everything else is considered to be an arithmetic operation here. Therefore, it will set condition codes, right? So, this stuff here, where do we go? This stuff here should just work. Jump if not equal, label, right? Because if the result of my shifting resulted in EDX being 0, then I would have a 0 like that. Make sense? Oh, everybody on board? You're watching the lecture online? Okay. And then, yeah, it's just the 3D is overwhelming. It's like 2D, it's like better effects and stuff. Okay, jump to label, and now we're done. Well, we want to return the result, and the result is in ECX. So we could have maybe used EAX all along, right? Yay! That wasn't so hard, right? Right? I hear the crowd going bananas here. Yay, it's cool. Okay, you guys are coding in assembly, guys. That's really fun. So here's like, effectively what we do is that we can take this Goto version here with the knife lookup, and we can translate it into this kind of weird Goto stuff, which is just like, hey, there's a loop here, we go to the loop, and we have our if branch. Now we've gotten rid of the whole loop, right? And we have the if sentence. And we know how to treat if sentences, right? We know how to convert if into something that's an assembly, right? Just create two branches and all that stuff, right? So we have effectively a way in which we can do stuff. So this is their version over here. This is we just, well, pretty much the same thing we did here. Shift things, we do the and L here. We did the tests, which is fine. And so the way it works is that it's just, oh, we're already got there, so we don't have to do it again. In general, you can take a do-while loop into the following. There's some body and there's some test. And you can convert it into this version here on the right, where you just have a label called loop, and then you put your body, and then you do an if sentence for the test, and we know how to do those things. So then you just end up with a version. So now, we've done do-while, but that's not what everybody uses. What about a while loop? How is it different?
You don't have like two.
So how would you piggyback on what we've already done to have a generic
Compare first.
Yeah, just move it up. You just have one thing at the head of that, you add an extra if sentence called if x is not true, go to done already. And then just do the rest of the do while loop. Okay? So we've already done this stuff, that's fine. And so this is the conversion of the integer. And now we have the question about a for loop. This is another version of counting the number of ones using a for loop. How does it work? Well, it just kind of looks at each bit at a time. And it goes until W size, which is 8 bits per byte in the integer. Creates a mask and all that stuff. Is this code equivalent to other versions? Well, let's look. Actually, in general, if you had a for loop, how would you convert it into assembly?
A while loop and a counter.
So you need the while loop and the counter, and you need to have conditions. Like there's some initialization needs to happen, and there's this condition that you need to make sure that you translate, right? Oh, that's exactly it. You have some initialization. You have your test to see if things should continue going. You have your update function, and that needs to be executed every round. And then you have your body. And what's happening here is that you just change it to the following code. Initialize. Well, test is true. Do the body stuff. Do the update, and go on. Sometimes you see code from inexperienced programmers that looks like this, and you're like, have you heard of a for loop? And then we're kind of done. So here's an example of how this would get translated. The initialization here is initialize I to 0. The test is, hey, did we reach W size or word size? Update is increment I by 1. Body is just the stuff that's inside the further brackets over here. And we're done. And then once we've managed to translate it into while loop, we can then do the other stuff, which is to move it into the do while loop through adding an initialization condition over there. So here's exactly what happens. If you take the C code from before and you look at what happens after this translation, this is what it would look like. And now, put your compiler hat on. What would a compiler do when it sees this code? Of course, it would look like, why is this code a different color? Right? Like you're in kindergarten, like, this is purple. Okay, so that's one thing. What would be the second thing it would notice here? It's a compiler. Remember, compilers are on steroids, trying to optimize the living uses out of things. What would it do?
I mean, do there need to be two if statements?
Yeah, that's a good question. Well, in one case, we don't want to execute stuff if this isn't true. In the other case, we want to see, do we continue? But in general, we kind of need them. But here, yeah.
It's going to read that it's not with I greater than W. It's going to read it as greater than or equal to.
Yeah, but that's fine. It's still equivalent, right? It's just kind of the Morgan rule or whatever you call it, right?
Move the update around and do it.
We'll move the update. Well, the update has to be after the loop, and it has to kind of be before the test, so it's kind of sandwiched a little bit. But it would look at this code, and it would look at it, and it would try to be a little bit intelligent. You're like, you set I to 0, and then you see if I is less than this constant over here, right? So it's going to kill this if sentence over here because it's completely spurious, right? That's what compilers are trying to do. They're just like, is this always going to be true? Why is there an if sentence for it? Right? That's what a compiler does. Right? It tries to find code that is dense. It tries to find code that's unnecessary or unneeded or completely spurious in any way, right? And it gets rid of it, like the mem set from Microsoft, right? So yeah, you don't need that. You don't use this after the fact, right? So it kills this guy right here. Of course, this is the ugly copper here. So we've done some work now on the condition codes and the registers and pieces. We kind of understand the CPU a little bit better now. We can even make programs that do stuff, right? Really interesting in programs that our parents are going to be excited about. They're like, look, it's counting, right? Or something like that, right? Oh, it's an infinite loop, look. Okay. So we'll get to slightly higher level things later. Okay? Now, let's talk a little bit about memory, right? So there's a little bit of review, and then I'm going to introduce just the stack principle here. So if you think of memory as being this really boring high school, right? It's the it's the high school where like there's just an infinite row of lockers. Right? Can you imagine being that like, oh, to go to my locker, it's like plus infinity. You go there and you die in your high school, right? Everybody dies in this high school. Okay, so what's going to happen is that, yeah, they're all going to be labeled, and there's going to be stuff inside of them, right? That's what you think about memory. And if you think about a memory address is effectively just being the key to the locker. I'm just trying to create like an analogy that's going to completely break down, of course, at some point. But it's very useful sometimes, right? So think about the key here as being the memory address. And think about there being some guy who says like, hey, I'm the guy who manages all this memory stuff here. And we're trying to figure out, we have this infinite set of memory here. How do we give it to different processes? How do we manage it to something? Do people just take their own locker? If there's infinitely many, it's probably not a big problem. But in reality, it's not infinite, right? So somehow we need to make sure that we have some rules about how memory is being accessed, right? So that's what this boring guy over there is supposed to be doing. Okay? So I'm tired of drawing actual lockers, so let's just think about these as being our lockers, and this is the memory. Okay? And I'm going to stash some like $9,000 that I plead the Fifth Amendment, not telling you like where I got them from. And I'm going to move them to some place here. I'm going to move them to locker 1301. Right? So that's what this particular method can do. If I can do that, I just open up and I get a copy. Of course, in this high school over here, whenever you like move stuff around, you get like this extra copy. So you take your $9,000 and you have like 2 versions of the $9,000. It's an amazing place, right? That's what digital world is like. This is why people don't get online piracy. You're like, it's a CD. I have 2 CDs and they're identical, right? Or a song or a movie or whatever. Okay, so I just took a copy of it. It's now stashed in this locker over here. Okay. Now I can also this is what it would look like in reality. We'd be taking a register or something like that. We'd be moving into memory address 1301. Right. Here's an actual immediate value. Here is the register. 2 different move operations that we've seen. All right. So I can also move the key into, why is there a purse? Okay, for some reason I have a purse. And for some reason I'm also out of battery. It's just very convenient right now, given that I don't understand why I have a purse. Hold on, yeah, the purse is supposed to be a register. Okay, hold on. I am seriously out of battery. Oh yeah, that's fine. Cool, thanks. So I can take the memory address and just stash it here on my like modem thing. So now there's the $9,000 in the back here in this memory location, and I know the memory location because I stored it in one of my registers. Okay, now I'm good. So what I'm trying to get at here is indirection, right? So for instance, I could say, take the memory address or whatever is in memory address 1301 and move it to EAX. And that takes a copy of this $9,000 and moves it into my purse over here. Or you could say, hey, I have this ECX register, I want to access the memory that it points to, and move that into EAX. So this is stuff that we talked about already. So if EAX here is the value 9,000, and ECX is the value 1301, there's really no difference in the computer whether or not this is a memory address or not, it's just in how we use it. This is something we've been through pretty well so far. Good, okay. So pointers to memory, I could also say like, hey, I want to move whatever this locker thing points to, I want to move it to my purse. So what's going to happen now is that it's going to look at like, hey, 1301, I'm going to go in there, and in 1301, I'm going to view that thing as a key. I'm going to pick it out from this locker, and I'm going to walk over to the next locker, and I'm going to pick up my $9,000 and move it into my purse. That's a pointer to pointer. And you can imagine you can have like a trail of keys in various lockers, and then eventually you find your stuff. You can also imagine how inefficient that would be in the end. Where you're like, oh, just keep opening stuff up, right? So that's what these are. Okay, of course, when we're copying pointers, when we're copying these keys, we're actually not copying the contents. Think about the following scenario. You have here $9,000 from one of your early exploits in locker 1296. And then like the wimpy version of you has $300 in the next one over, right? And what you're going to do is you're going to say in C, you're going to say something, hey, I have like a pointer to locker 1296. So I have the key to this one here. And I also have the key to the next one over here, my wimpy one. And then I do this. What happens?
Now points to the old 96.
Yeah, now I have 2 keys that both point to the same locker, and I've lost the key to the $300 locker. Right? I haven't copied any contents, right? Now, of course, when you're in some higher level languages, maybe it's implied that you copy all the contents of the classes and so forth. In C, there's absolutely nothing like it. You just copy the pointer itself. And you're on your own to make sure that whatever's underneath there, or whatever's pointing to a structure like that, if you want to move those things, you do it yourself. So the right thing to do would be to do this, to say that whatever B points to is now supposed to contain whatever A points to. This is the equivalent of the operation saying like, hey, let's take these $9,000 and move a copy over here. Of course, the $300 now vanish from the place here. Not doing it there, and now we have money. It's like so much fun having money in a digital world, right? Such a meaningless quantity. Okay, so how does one create a key? So far, we've pretty much seen like these local and static variables, right? We've seen that like you could do something like this, like, hey, I love 485, which is the old name for this course. And I can create like there's like a pointer over here. This is the buffer, and it somehow it just mysteriously gets created. So right now, buff is a local variable. And a local variable has to be allocated somewhere, right? You have to have memory somewhere that stores this string, I love CS453. Right? I'm going to repeat this phrase very often so that you guys are like, yeah, that's something that I love. And you're going to be in this year, and I love, there's some course number that's coming back to haunt me in this sleep, but I really like it, right? So, okay. 453. So, what we have so far is effectively an abstraction that says, hey, I want some memory, and I kind of want it right now. For my local purposes, within this function, I want to have this buffer. So we're going to introduce the notion of a stack, right? So it is a portion of the global memory that's governed by a special principle, which we'll now get to, right? And as I have not mentioned before, stack in x86 grows down. Now, it did mention this a little bit because we were going up, like we added 8 to EPP and so forth to get to older variables. So for some reason, like the stack on x86 grows, it's like an Australian stack, like it's like upside down, right? If you push something to it, it's like you have to push it over here. There's actually a good reason for this. So if you actually look at the memory layout for x86, let's say this is the layout, and like here are the higher order addresses. So I turned it around from what I'm used to, and here are the smaller addresses over here. We have a stack that goes over here, and it grows in this direction. Why does it grow in this direction? Because here, somewhere, there's the actual program, and here is something called the heap, which is the second set of things that it could allocate. And that grows in that direction. So you have a stack that's growing from here, and a heap that's growing in this direction. They're growing against each other. Now, why would that be a good idea? The intent is that you don't know whether or not you're going to use a lot of stack space or a lot of heap space ahead of time. If they were growing in the same direction, you'd have to make an arbitrary decision to move things like this, right? Here's a stack, and it grows in this direction. And then there's a heap somewhere here, heap, and it also goes in this direction, and here's the program. So whichever one runs into something else first runs out of memory, right? So it's possible you'd have a stack, and it just goes in there and hits the heap, and you have to crash, even though all of this is blank and empty. You can't jump over something. So that's why we have things growing against each other. Does it make sense? Okay, so stack grows down on x86 Intel. So here's a little memory manager again. He's like, hey, yo, okay, so there's all this stuff, and here are the higher order addresses. Instead of FFFF, let's just make it 4 nines. And what this guy does is to assign you memory addresses. This guy is responsible for your stack, right? What he's going to do is he's going to point here. This is his kind of stack pointer hand. He's going to point here at the earliest available memory you might be able to use. And now you're going to say, like, hey, I have this function here, it's called blah. This is a terrible name for function. And I have another thing called function for no good reason, which is also terrible. And this one requires 12 bytes of memory. The other one requires 16 of things that are called A and B inexplicably. Okay? And so what's going to happen is that you have your stack. You can think about this as being the bottom of your stack, like an actual data abstraction here. You're going to add stuff on top of it. And what the memory manager is going to do is going to say, like, hey, okay, you're executing this blah thing here, and you need 16 bytes. Well, let me move my stack pointer hand to the left. Right? So I went from what has happened here. Go back. Okay. I moved it here and I allocated 16 bytes for this buffer, right? This is 16, there's 4 bytes in each of these buffers, right? And now I go to my function over here. What's going to happen is that I'm actually going to push something onto my stack. I'm going to push information about how on earth I get back here. So now I'm executing function over here. I'm in function, and everything's good. Where's my function thing? It's here. And it also needs 12 bytes of memory. So it's going to be like, okay, I'm going to take these 12 bytes of memory and copy. So you see how we're kind of like taking up more and more memory. And all this memory management needs to do is just like point in one place. It's kind of cool, right? And now we're done with this, like, look, now we're adding I here, which is another 4 bytes, so we're going to do the green thing over here. And now we're done with this function called function, okay? So now we're going to need to somehow go back here, right? So there are 2 ways in which we could accomplish that. We could go like, oh, okay, there were like 12 bytes for B and there were 4 bytes for I, so I'm going to subtract that from my stack frame and then go back. But that can be really tedious, especially when you have things that are growing dynamically, or if you have to jump out from a function really early. So instead, what we do is that we actually use 2 hands. One of them is the stack pointer, just like what we saw. The other one is a pointer to where we were last time. So if we go back here, there will be a second hand here pointing at 99 forward. That's the base pointer. That's the frame pointer. That's the EBP that we've been talking about so far. Make sense? So whenever we're done with a function, all we do is like, oh, okay, I'm done with this function over here. I'm not going to just like make my stack pointer point to my frame pointer, and then I need to somehow know what my previous frame pointer was. So now I'm in trouble. So that's why we actually not just push the return address onto the stack, we also push the last frame pointer. So now we like pop it off, and now we know where we were, and we're back to normal. So when we make a call to a function, we could be doing all sorts of stuff with the stack, but when we're done, our stack pointer and frame pointer are just like what they were before. Cool, huh? So now we continue here, and everything is good, and all these animations. So now we can ask, you have a question, or you? Okay, scratchy. Okay. So the question is like, is it enough? Of course, like, have you heard of what's it called, the Godwin law of headlines? Any headline that asks a question, the answer is no. Okay? Name me a counterexample. Can you name me a counterexample? Huh? See? Okay. It's not really sufficient for everything that we need to do. We can't just have a stack. That doesn't quite work. So, for instance, what if I wanted to access something from my parent function? Well, what if I just wanted to persist something? Like I want to be able to like write something to a display. I want to know what the display looks like right now. Or I want to have a file and I want to just keep it around and do stuff with it from different functions. Just having a stack is not quite enough, right? Now, there are some that are going to argue that like, well, actually you could just code everything in Lisp and and then I just zone out and think about other things while this person finishes, right? So you would love to be able to have very large data. You'd love to be able to reach stuff from parent functions and all this stuff. So that's why we have this thing called the heap. The heap is kind of for these longer-term persistent data structures. And in fact, modern programs mostly use the heap. They don't use the stack as much. Okay? So that's called dynamic memory allocation. You can think about this as being new and delete in C++, or malloc and free in C. Of course, functional programming languages don't really have this, except they kind of do now. Right? They have like little things, side effects that they can create. They all claim they don't, but they do. So. Anyway, so how does that work? Dynamic memory allocation works as follows. Now, instead of just assigning the next thing, like having just one pointer that's pointing to the next thing that's available, you're just going to assign data to whatever is available, right? So you actually have like a big kind of like a set of lockers over here, and you see like, oh, actually you need like 2 adjacent lockers. Yeah, okay, I have 2 right here. You get memory address here, but 221 and 222. Okay? That's what your dynamic memory manager is going to do. So for instance, if we have the program here with 3 pointers A, B, C, and we have, oh dear, We have another pointer called C here, character pointer here, C and D. Yes, I know. And we allocate 4 bytes of memory for A. Then those are the 4 bytes of memory. They're available. And then we have B here, where you can also allocate that 4 bytes of memory. That's what Malin does. And it can be from wherever, as long as it's not occupied by someone already. Making this stuff is actually harder than it looks, because now we might have the following problem. We could say, like, C is not a copy of A, so C also points to the same memory address. And now we do a free of A, meaning that A is not available. But I still have a pointer called C that's pointing to here. So now I can't use the C pointer. Okay? In fact, I still have a pointer A that I shouldn't use either, right? But what if I do now malloc of 5, right? Well, according to the dynamic memory manager, there were 5 consecutive bytes here that were available. But we still have a C pointer somewhere. And that could be misusing that, right? If I'm here and I write to D, what happens? It's unallocated, right? We haven't specified. We didn't initialize D. Looking at this slide should convince you that when you're writing code, always initialize your variables. When you free something, make sure nothing else is pointing to it. And also appreciate that when you're asking for memory, it's actually a bit of work, because you have to align things up, right? But for instance, like in this last thing here, if I had 4 bytes over there and 4 bytes over there, and now I ask for 2 bytes. There are 2 bytes available in memory right now, but I will be rejected because there are no consecutive 2 bytes available. And I can't move memory that I've already committed in this scenario. This is a plot thicket. We will actually have a whole lecture dedicated to just how memory management works in C and Windows and others, in Linux and Windows and others, where we're talking about how you actually tackle these challenges. But this is just kind of to give you a taste of that. Now, what do we want to do? So here's the locker analogy. If you really want to like go overboard, you'd be like, oh, memory side lockers. It kind of works pretty far, and then eventually, like, as I started adding more, like, memory leakage is like forgetting to tell the manager that the locker was free, right? It's like you kept the key and you went home, right? There's all sorts of things that you can look at this, but eventually this analysis is going to break down. So what I wanted to do starting next time is to talk a little bit more about the stack, how exactly it works from like an assembly level, right? So talk about the stack pointer and stack bottom and so forth, but we're kind of out of time for today. So any questions before we close? Yes?
Just trying to make sure I remember this one correctly. When you put the 9,000 into the register, why did you not put a $sign?
I intended to. Well, it depends on what the intention is. If I just say move, so if I write the following expression here in the Intel syntax, in the AT&T syntax, if I move L 9,000 to EAX, what this means is go to memory address number 9,000, grab me what is there, put in EAX, right? If I move L 9,000 to EAX, it means, oh, move the immediate value 9,000 into register EAX without touching any memory. So this dollar sign makes all the difference. As we all know, dollars make a lot of difference.
So that's the one.
So maybe I miswrote it. It's very possible that I missed the dollar sign here or something like that, given how this fusion of slides came about. Yeah?
I was just double checking.
Yeah. No, but this is a very important distinction, so that's brought out. Other questions? Yes?
Why do you use a different window on the website?
Great question. Any other questions? Yeah, I'll fix that. It's from last year. I'll update all of it. Cool. Okay. See you. See you Wednesday, right? There's no class on Monday. Isn't there Labor Day? Yeah. Okay. So enjoy your exercise, and office hours start at 1 if you want to.
Due this Friday or this Friday?
It's due on Tuesday night. Yeah. Yeah. I had like 3 different deadlines in different documents. I'll try to consolidate them a little bit.
Okay, so